Right. So, before the break we were talking about the Ito's lemma and I explained the concept behind it. Now, we move on to the stock price distribution. Now, stock price distribution can be handled at two time scales. We have a stock price model at the infinitesimal time scale, and then we extend that model to a finite time scale. Why there is a difference between the two will become clear as we move along this particular topic. So, let us start with the first one, the infinitesimal time model. Remember, this model holds for very small time periods, that I strongly emphasize. The model that I am going to discuss now holds for very short time periods. Why it is so, we will come back to it. Now, the assumptions, of course, is the standard assumption that the stock prices follow a Markov process. This is consistent with the weak form of the efficient market hypothesis, which assumes that the current stock price encodes all the history of the stock, all the price history of the stock, and therefore, we need not go beyond. We need not go back in time to explore more about the stock price. Whatever is today's stock price covers everything or incorporates all information about the prior period behavior of the price. So, that is in a nutshell, that is what we form by the what we mean by the weak form of the market efficiency, and that is what makes the process Markovian. There are two fundamental assumptions. The first assumption is that the expected percentage return required by investors or over an infinitesimal time period dt. Infinitesimal is important. Infinitesimal time period dt from a stock is independent of the stock's price. In other words, whatever the stock price is, the return over a small period of time expected return by expected by the investors is constant. And the second is that the variance of the percentage change in stock price. Variance of what? Variance of percentage change in stock price is in the same time dt is also independent of the stock price. So, investors expect the same return, percentage return. If the stock price is 100 or the stock price is 200, the percentage return over a given period of time expected by the investors, provided the time interval is small, is the same, and the variability of that the perception about the variability of the return is also same. How does it translate to figures? Let us see. The expected percentage return required by investors. What is the expected percentage return? ds by ds we are using this formula. The justification or the rationale for using this formula is provided by dt. We can use this formula if dt is small. I will come back to it. ds upon s is the percentage change in price. ds upon s divided by dt is the percentage change is the return over period dt. E gives us the expected return. So, expected value of 1 by dt into ds by dt is constant, which is written as mu. This gives us, because dt is non-stochastic, we can take it outside the expectation operator and we get E of ds upon s is equal to mu dt. In other words, we can write ds upon s as mu dt plus some randomness term which has a 0 expectation value. Now, come to the variability. What does it say? So, standard deviation of ds upon s is independent of s. So, we can write it as sigma root dt. The variance or the standard deviation of the percentage change in stock price, this is the percentage change in stock price ds upon s in a short period of time dt is the same irrespective of the stock price. So, the right hand side must be independent of the stock price. The standard deviation of this quantity is independent of the stock price, which gives us this. Combining the two expressions, we can write ds upon s is equal to mu dt plus sigma dw, or this is equal to mu dt plus sigma z under root dt. dw can be written as z under root dt. It is easy to check, it is very simple to check that this equation, this stochastic differential equation gives us the correct parameters. For example, E of ds upon s is equal to mu dt is straightforward, because the mean of this quantity dw is 0 or mean of z is also 0. So, in any case the expected value of this is mu dt, which is what we wanted. And about the variance of the standard deviation of this, sigma of ds upon s, this is non-stochastic. So, it has a standard deviation of 0, and as far as this is concerned, the standard deviation of this is 1, and therefore, sigma the standard deviation of this entire quantity is sigma root t. This is precisely what we wanted, sigma root dt. This is precisely what we wanted. So, this equation gives us the correct parameters. This is consistent with our assumptions. So, this particular equation constitutes the stock price model for infinitesimal small time periods. Now, we move from the infinitesimal time periods to a relatively long time period. For this, what we do is we invoke Ito's lemma. We write g. You remember, g is a function of a stochastic process. We write g as log of s. Clearly, g is continuous and clearly g is twice differentiable. So, that is not a problem. Where s is what? S follows this particular stochastic process which we have just outlined. I repeat, g is a dependent variable which is a function of s, and s which is a function of s given by log of s, and s itself follows the stochastic differential equation given by this expression. Then we have, by standard calculus, the first derivative of g with respect to s is 1 by s, the second derivative of g with respect to s is minus 1 by s square. The derivative of g, because this is not there is no explicit time dependence, therefore, dg upon dt is equal to 0. Putting these values in the Ito's equation, we get dg is equal to d of log s, because g is equal to log s, is equal to mu minus sigma square upon 2 into dt plus sigma dw. I have simply substituted the values of dg upon ds, d to g upon ds square, and dg upon dt in the Ito's equation, nothing more. On substituting these values, I get this. So, what does this say? It says that dg follows a Brownian motion or a generalized Wiener process with a drift of this expression and with a scaling of sigma. And now, dg is equal to d of log s. If we integrate this between the limits s0 and st, we get log of st minus log of s0. Log of st minus log of s0 is normally distributed with a mean of mu minus sigma square upon 2 into t and a variance of sigma square t. I repeat, log of st, what is d? D is the change. So, log of st minus log of s0, if you integrate this, log of st minus log of s0, now this term is constant. So, you can simply integrate dt between 0 and t. So, that gives you capital T, and similarly if you integrate this, you get sigma square w t. Now, that gives you what? That gives you that log of st minus log of s0 is normally distributed with a mean of mu minus sigma square upon 2 into t and with a variance of sigma square t. In other words, log of st is normally distributed, because this is constant, this is information known at t equal to 0. Log of st is normally distributed with mean of log of s0 plus mu minus sigma square upon 2 into t and a variance of sigma square t. Now, this is the finite time model. This is the finite time model for a stock price. We have obtained it using Ito calculus and then integrating it. the advantage facilitated by this is that this expression being constant, it is easy to integrate, and similarly this integration gives you dw integral of dw, which is wt minus w0. W0 is 0. So, wt and wt has a variance of t. So, we get sigma square t as the variance. This does not contribute to the variance because this is deterministic, and therefore, d of d means log s t minus log s 0. Log s 0 can be taken to the right hand side, and we get log s t is normally distributed with a mean of log s 0 plus this expression into t and a variance of sigma square t. Now, the important thing is that log of s t is normally distributed. What does it mean? It means s t is log normally distributed. Hence, we arrive at the famous log normal distribution of stock prices. Log of s t is normally distributed. Therefore, s t must be log normally distributed, and that is what is the log normal distribution of stock prices. Now, let us talk. We so far talked about the distribution of returns. Sorry, we have talked about the distribution of stock prices. S t is the stock price. We have talked about the distribution of stock prices. Now, we talk about stock returns. We define logarithmic stock return as 1 by t log s t upon s 0. This is the standard definition of logarithmic return. Using the expression what we had earlier, we know that log of s t is normally distributed with a mean of log s 0 plus this expression mu minus 1 by 2 sigma square t and a variance of sigma square t. Therefore, if you simplify this, you find that the logarithmic return is normally distributed with a mean of mu minus 1 by 2 sigma square, mu minus 1 by 2 sigma square and a variance of sigma square upon t. Variance of sigma square upon t, because this 1 by t comes here, this t goes from here to the left hand side, it becomes 1 by t, but once you scale a variable by t or 1 by t, the variance gets scaled by 1 by t square. So, this gets scaled by 1 by t square and you get sigma square upon t. So, remember, the stock price is log normally distributed, but the logarithmic return is normally distributed. This is very important. Stock prices are log normally distributed. Logarithmic returns on stock prices are normally distributed. Now, why did I say that the earlier model was a model that was for infinitesimal time periods, and this model is for a finite time period? The answer is contained in the slide. We define the logarithmic return over time dt as 1 upon dt log change in s dt, that is the final price upon the initial price. So, if you simplify this, you can write it in this form. S 0 and S 0 cancel out, you get the same expression S dt upon S 0. If you simplify it further, you can write this is the change in stock price S dt minus S 0, you write it as ds, and this is the original stock price S. So, I can write it in this form. Now, this is of the form log of 1 plus x. Log of 1 plus x has the standard expansion x minus x square upon 2 and so on. So, we expand it as a Taylor series. This 1 by dt remains as it is, and we have ds upon s minus 1 by 2 ds upon s whole square, and this continues. Now, if you look at this and if you compare with the expression that we had earlier for ds upon s, the infinitesimal model, in the infinitesimal model we confined ourselves to the modeling of ds upon s, which is nothing but the first order approximation of logarithmic return. You can see here, the full expression is the logarithmic return. If you confine yourself to the first order expansion, that is, you confine as you truncate it at this point, you get what is simply the model that we used in the infinitesimal case. Therefore, the infinitesimal case is the model when we are approximating the logarithmic return by a first order Taylor expansion. First I reiterate, we are approximating the logarithmic return by a first order Taylor expansion, and that obviously can be done only when this expression is small. So, that is the relation between the two models. Now, I have used the Ito equation or the Ito lemma to arrive at the log normal property of stock prices. Again, I invented the expression G is equal to log S. In other words, it is slightly obscure insofar as from where I get this expression log S. There is a more explicit and a more intuitive approach which is provided by the Fokker-Planck equation. The Langevin equation, you see the stock price equation this equation is a stochastic differential equation. It can also be written in this form, which is usually referred to as the Langevin equation. This is Gaussian noise, a delta correlated Gaussian noise. It is the same thing. In some sense, this eta t is the derivative of Brownian motion, although as I mentioned earlier also Brownian motion is not differentiable at any point. Therefore, strictly speaking, there is no mathematical derivative of Brownian motion, but this serves something like a derivative of a Brownian motion. Some at a rough level, at a simply at a conceptual level, it constitutes the derivative of Brownian motion. That is just for the understanding, although technically it is not correct. But anyway, this equation is of the form Langevin equation is stochastic differential equation. We start with a relatively more general form of this we write this equation in the general form dxt is equal to fx dt plus gx dwt. We will arrive at the Fokker-Planck equation for the general curve, and then we will construct the Fokker-Planck equation for the stock price, and finally we will solve that equation. Now, the important thing is that this Fokker-Planck equation is the equation for the conditional probabilities. So, you cannot there is no probabilities here, but this translates to an equation for probabilities. Let us go through it. We discretize it differential equation and we get x t plus dt, that left hand side is x t plus dt minus x t, and the right hand side can be written as fx dt plus gx, and instead of dwt we write z under root dt, which is obviously allowed. So, now we take any arbitrary function of x t and we write the first derivative with respect to time as a limit. This is what we get, g x t plus dt and minus this divided by the standard definition of derivative. Before doing the Taylor expansion, we write x t plus dt is equal to this expression, x t plus dt is equal to x t plus f x dt plus gx g under root dt. We substitute this value here. Now, we do the Taylor expansion. We do the Taylor expansion of g around this expression, that is these two expressions are same. We do Taylor expansion around this. So, what will we get? The first term will be g dash x into this whole expression plus 1 by 2 g double dash x into this whole expression whole square, and so on, and dt remains as it is, the limit remains as it is. Now, this is what we had from the previous slide. We simplify this, and what do we get? G dash x into fx dt plus g dash x gx z dt, this into this, plus this expression plus order dt to the power 3 by 2. From where do we get this? We get this from here. This into this will give me d to the power 3 by 2, and this whole square will give me dt square, which both the terms will throw out. In other words, both the terms are encapsulated within this expression. So, what we are left with is this into this into this, plus this into this. This squared obviously gx square z square dt, gx square z square dt. This when we open the square, dt square will go, and root dt into dt being of power 3 by 2 will also go. Now we make the Ito assumption. What is the Ito assumption? The Ito assumption is, you see, let us go back a bit. We wrote the area, when we did the area thing, we wrote it as y dx, or we in summation we wrote it as yi dxi. What was yi? It was the initial value, and dxi was the forward difference. Suppose this is the curve, this constitutes my yi, and then I multiplied by dxi, which is the forward difference. yi is the initial value, and this constitutes the forward difference. This is called the Ito assumption. Now, it is very important to note that this is not unique. You can use, you see, you can use yi as the initial value, you can also use it as the mid value, you can also use it as the terminal value and the backward difference. All the approaches would be correct. Of course, the equations that we arrive at would be different, but the physics would be equally well described. That is the important thing. The underlying system would be equally well described if we take the final value and work back and take the backward difference, or we take the average value, or we take the initial value. The initial value assumption is known as the Ito assumption, where we take the initial value of y and multiply it by the forward difference. If we use this valuation, if we use this value, we can do some simplifications. Then E of gx into z, this gx and this z become independent of each other, and because they become independent of, because of the Ito assumption, these become independent of each other. Gx and z become independent of each other, and they can be decoupled. And when you decouple them, you get E into gx, E of z, but E of z is equal to 0, therefore this term has an expectation of 0. Similarly, when you use the same logic here, you decouple gx square and z square, E of gx square into E z square. E z square you know very well is 1. So, this becomes E gx, and we now use these two expressions. Putting these two expressions here, what do we get? We get E of this x in the left hand side is equal to E of, now this expression remains, right, and this expression goes to 0 because the expectation of this is 0. This expression becomes 1, therefore, we have 1 here, and this dt and this dt and this dt cancel out. So, we are left with these two terms only, and this is thrown out, and we have dt, these two terms you take dt common, cancel it with this dt, and dt tends to 0 also goes, and we are left with g dash x f x dt and g double dash x by 2 g x whole square. So, this is what we are left with. Now, we do the expectation values. Now, standard definition of expectation value is given in this equation. Integral of the function with respect to the probability distribution and the product of the function and the probability distribution. We have integral, as you know, x p x dx. This is the standard expression for the expectation value. This is precisely what is here. Instead of x, we are having f w, which because we are talking about functions of x. So, d w into f x, and this holds for the derivatives as well. It is absolutely same. Now, what we do is we substitute, as I mentioned, g x is an arbitrary function. Now, I choose g x as the delta function x minus capital X. I choose g x as the delta function x minus capital X, the Dirac delta function, which assumes is just like a spike. It will have a spike at x equal to capital X, and it will be 0 elsewhere. In other words, when we do the integration, it captures only those values for which x is equal to capital X, and it throws out the rest of the values. So, when we do the integration of this various terms, remember what are we doing? We are substituting g x equal to delta x minus capital X. When we do the substitution here, this is simple. When we do the integration, this delta w minus omega minus x will be replaced by small x, capital X. All the rest of the terms would be thrown out. Only the terms where these two are equal will be retained by this integration, and we get this. This omega will be replaced by x. That is the effect of this delta integration, all the other terms will go. So, in effect what we are doing is we are evaluating these expectations at the point capital X, at the point capital X. That is the important thing, that is the net result. It's for the second term f x delta dash x minus x, we write it as, we do an integration by parts. When we do an integration by parts, the derivative shifts from the delta function to the first function, this function, and we end up with this particular expression. And similarly, when we do the integration of this expression, or work out the expectation of this expression, again when we do the expectation of this expression, again we do a twice part integration by parts, and we get the second derivative of the first function, and this function derivative of this function goes, this function remains as it is. When you integrate this with this delta function, this becomes g x, this becomes p x. That is precisely what is here. When you substitute these values in this equation, you get what is called the Fokker-Planck equation. So, this is the Fokker-Planck equation for corresponding to the general Langevin equation, or the general stochastic differential equation, dx is equal to f x dt plus g x dw. This is the, you see, please note this point, this is an equation for probability, this is an equation for probability, and the Langevin equation was for the displacements. Dx is equal to f of x dt plus g of x dw. This is where we started with, and we now have an equation for the differential equation for the probabilities. Remember, this f x and this g x are nothing but this f x and this g x, the same functions. Now, for the stock price model, for our stock price model, what is our stock price model? This is our stock price model. For this stock price model, this particular Fokker-Planck equation takes the form this, where you see f x is nothing but mu s t and g x is nothing but sigma s t. So, we are substituting f x equal to mu s t, and we are substituting g x equal to sigma s t. So, g x square is equal to sigma square s t square. If you solve this equation, the result that you get is this particular expression. This particular expression, if you look carefully, is the PDF of a log normal distribution. Therefore, we have established that the stock price follows a log normal distribution. You can see here the logarithm appearing. So, this is for the log normal distribution. This is the probability distribution for log of s, or the s t probability of s. This is the probability distribution for s, and s follows a log normal distribution, as you can see by this log of s upon s dash. So, this is not the normal, please do not mistake it for the normal distribution, it is the log normal distribution, it is the PDF of the log normal distribution. So, s is log normally distributed, not normally distributed. I have put the derivation of the PDF of log normal distribution in this presentation, in this PPT, and I leave it there. So, those interested can obviously refer back to it, but this is the PDF of the log normal distribution. How to solve this Fokker-Planck equation? Well, it is solved by a transformation of variables, which enables us to transform this equation to a diffusion equation, and thereafter diffusion equation, in fact we have already solved earlier. We can use Fourier transform for solving the diffusion equation and arrive at this particular solution of the Fokker-Planck equation. The derivation also of this Fokker-Planck equation I have put in this presentation with the boundary conditions. Everything is there, the various steps involved are there in this presentation, and the various substitutions are there, boundary condition, revised boundary conditions are there. You make substitutions at two levels. First level, you make certain substitutions, you arrive at a function f x of f of x and tau, and then you make a second substitution, you arrive at a function of g x and tau. Now, g x and tau function g of x and tau satisfies the diffusion equation, which therefore, the solution of g x tau can be directly written or you can work it out using Fourier transforms or any other method for that matter, and you end up with when you make the reverse substitutions, you end up with this particular solution. This is the solution for g x and tau. As I told you, this way g x tau satisfies the diffusion equation, and therefore, it has the solution this one, and when you make the reverse substitutions, you end up with the solution for p, and if you put p equal to xi equal to log s, this solution turns out to be a normal distribution. Now, this is interesting. Another point, this is the log normal distribution, as I mentioned. P s t s dash t is log normal distribution. What happens if you put xi equal to log s? If you put xi equal to log x, you get the normal distribution PDF. Therefore, the log of s is normally distributed and s is log normally distributed. Thank you.